China's artificial sun breaks nuclear fusion record. Date: January 25, 2025. Overview. On December 30, 2024, China's experimental advanced superconducting Tokamak East, commonly known as the artificial sun, achieved a remarkable breakthrough in nuclear fusion research by successfully containing plasma for 1066 seconds, which is over 17 minutes. This milestone marks a significant advancement in the pursuit of practical nuclear fusion energy, a goal that has challenged scientists for more than 70 years. Key achievements. 1. Record-breaking duration. The East reactor's new record of 1066 seconds of plasma confinement more than doubles its previous achievement of 403 seconds set in 2023. This extended duration is critical for reaching ignition, the point at which a fusion reaction can produce more energy than is consumed to initiate it. 2. Technological upgrades. This breakthrough was made possible by significant upgrades to the East reactor. Notably, researchers doubled the output capacity of the heating system while ensuring stability within the reactor. These enhancements will facilitate continued research and development in fusion technology. 3. International collaboration. China plays a pivotal role in the International Thermonuclear Experimental Reactor ITER project, contributing approximately 9% of its construction. Despite ITER facing delays and budget overruns, advancements at East are anticipated to benefit ITER's operations, as both projects utilize magnetic confinement to achieve fusion. Sustainable energy development. The achievement at East is hailed as a landmark milestone towards sustainable and clean energy sources. The successful plasma confinement not only enhances China's position as a leader in nuclear fusion research but also contributes valuable insights to the global scientific community. Researchers from around the world are collaborating with Chinese scientists to better understand and advance nuclear fusion technology. Timeline of events. 2006, East begins operation as a test facility for nuclear fusion technology. 2023, East achieves a plasma confinement record of 403 seconds. December 30, 2024, East sets a new record by containing high confinement plasma for 1066 seconds. Detailed insights from various sources. Source 1, Quartz. Quartz reported on the achievement, emphasizing the significance of the 17-minute plasma confinement as a crucial step toward practical nuclear fusion energy. It highlighted the role of researchers from the Institute of Plasma Physics ISIP and Hefei who are dedicated to overcoming the long-standing challenges of fusion technology. Source 2, SciTech Daily. SciTech Daily provided context on East's history, noting its establishment in 2006 and its evolving role as a testbed for fusion technologies. The source underscored the importance of ongoing research in achieving a cleaner and more efficient energy future. Source 3, Popular Mechanics. Popular Mechanics focused on the technological advancements that enabled the breakthrough, detailing how the upgrades to the reactor's heating system contributed to the extended plasma confinement. It also pointed out the collaborative efforts between East scientists and the ITER project, emphasizing the global nature of fusion research. Conclusion. The recent achievements at China's East reactor represent a pivotal moment in the field of nuclear fusion with implications for sustainable energy development worldwide. As researchers continue to refine the technology and methods used in fusion experiments, the potential for nuclear fusion to become a viable energy source in the future becomes increasingly tangible. With ongoing collaborative efforts and technological advancements, East is poised to remain at the forefront of nuclear fusion research, paving the way for a cleaner energy future. The recent achievement of China's experimental advanced superconducting Tokamak East, dubbed the artificial sun, marks a significant milestone in nuclear fusion research. The reactor achieved a record plasma confinement duration of 1066 seconds over 17 minutes on December 30, 2024. which is more than double its previous record of 403 seconds set in 2023. This development is crucial because extended plasma confinement is necessary for reaching ignition, the point at which a fusion reaction generates more energy than is consumed to initiate it. Key insights and counterintuitive information. 1. Significance of plasma confinement. While the record time of over 17 minutes is impressive, the counterintuitive aspect lies in the fact that achieving ignition requires sustained plasma confinement for thousands of seconds, not just the 1,066 seconds achieved. This means that while the recent record is a remarkable step forward, much work remains to be done to translate this achievement into a practical energy-generating fusion reaction. 2. Technological upgrades and stability. The advancements that led to the record were due to upgrades that doubled heating output while maintaining stability. This achievement may seem straightforward, yet it highlights the delicate balance needed in fusion technology. Doubling output without compromising stability is a significant engineering feat which underscores the complexity of fusion research that often goes unnoticed. 3. A collaboration with ITER. China's involvement in the ITER project, which is facing significant delays and budget overruns, adds an interesting layer to the narrative. Although the ITER project is considered the world's largest fusion experiment, the progress at East suggests that smaller, more agile research facilities might be capable of making faster strides in fusion technology. This could imply that the path to viable nuclear fusion energy might not solely rely on massive international collaborations but could also be advanced through independent projects like East. 4. Global implications of local achievements. While the achievement at East is celebrated as a national success for China, it also has global implications. The research and advancements made at East are expected to inform and assist the ITER project and the broader fusion research community. This suggests that local advancements can have a ripple effect, influencing global scientific endeavors in unexpected ways. 5. Perceptions of fusion energy. Public perception often views nuclear fusion as a distant and unattainable goal akin to science fiction. However, the rapid advancements made by East challenge this notion. While the timeline to practical fusion energy remains uncertain, the breakthroughs achieved signify that the pursuit of fusion may be closer to realization than previously thought. 6. Investment in fusion research. The immense investment in fusion research may evoke skepticism about returns on investment. However, the counterintuitive takeaway is that every incremental advancement in technology, like the doubling of heating capacity, has the potential to lead to significant breakthroughs in energy generation. This perspective encourages ongoing investment, despite the slow and often frustrating pace of progress. 7. Interdisciplinary collaboration. The success at East arose from collaboration across various scientific disciplines and institutions. This highlights the counterintuitive idea that breakthroughs in complex fields like nuclear fusion do not solely rely on singular expertise but benefit from diverse inputs and shared knowledge across disciplines. 8. Potential challenges ahead. The optimistic tone surrounding the achievements at East may obscure the significant challenges that remain. While achieving a new record is promising, the scientific community must still tackle formidable challenges related to energy input and output ratios, materials that can withstand extreme conditions, and the scalability of fusion technology for practical energy production. In summary, while East's achievement of maintaining plasma confinement for over 1,000 seconds is a momentous event in nuclear fusion research, it also reveals counterintuitive insights regarding the nature of scientific advancement, the complexities of fusion technology, and the collaborative efforts needed to make practical fusion energy a reality. The path to sustainable energy through fusion is still fraught with challenges, but the progress made offers hope for future developments in clean energy solutions. The report on China's experimental advanced superconducting Tokamak East, known as the artificial sun, achieving a historic milestone in nuclear fusion research, is significant for several reasons. While many readers may focus on the impressive record of plasma confinement for 1,066 seconds over 17 minutes, there are nuanced elements within the report that hold considerable importance, yet are often overlooked. 1. The concept of ignition and its implications. One of the most critical points that may be missed by the casual reader is the significance of achieving ignition in nuclear fusion. Ignition refers to the point at which a fusion reaction produces more energy than is required to initiate it. The report emphasizes that the extended plasma confinement is a prerequisite for reaching ignition. This is significant because ignition is the holy grail of nuclear fusion research. It represents a self-sustaining reaction that could lead to practical and limitless energy production. Most discussions around fusion energy focus on the dream of clean, sustainable energy. But the technical hurdles to achieving ignition are profound and complex. Understanding ignition's role illuminates why East's advancements are not just incremental but potentially transformative in energy science. 2. Technological upgrades and their broader impact. The report highlights that the recent success at East resulted from technological upgrades, particularly the doubling of the heating system's output. This detail is significant as it reflects the iterative nature of scientific progress. Advancements are often built upon previous work, and innovations in one field can have cascading effects across various applications. The ability to maintain stability while increasing heating output is a complex engineering feat, suggesting that the technological breakthroughs achieved here could influence other areas of research, including materials science, engineering practices, and even other forms of energy production. 3. Collaboration with ITER and its global significance. While the report notes China's participation in the ITER project, the implications of this collaboration are profound and may not fully resonate with readers. ITER is a multinational project aimed at demonstrating the feasibility of fusion energy. With ITER facing significant delays and budget overruns, advancements at East are particularly noteworthy. The collaborative nature of fusion research, with scientists from around the world working together, underscores the idea that energy challenges transcend national boundaries. This international cooperation could lead to accelerated advancements in fusion technology, ultimately benefiting global energy security and sustainability. 4. Historical context and future trajectories. The timeline provided in the report illustrates the historical progression of East from its inception in 2006 to its recent achievements. This context is crucial in understanding the long-term commitment required to achieve breakthroughs in fusion technology. The fact that East has progressively improved its confinement times indicates a trend of continual enhancement in learning. This long-term perspective is often neglected in discussions about fusion, where the focus tends to be on short-term results rather than the foundational work that precedes major breakthroughs. 5. Implications for sustainable energy development. The report emphasizes that the record-setting achievement at East is a landmark step towards sustainable and clean energy sources. However, the broader implications of this statement are often overlooked. Achieving practical nuclear fusion could revolutionize the energy sector by providing a nearly inexhaustible source of energy with minimal environmental impact. This could fundamentally alter energy markets, reduce reliance on fossil fuels, and contribute significantly to combating climate change. The connection between fusion research and global sustainability efforts is a critical aspect that deserves deeper consideration. 6. Cultural and nationalistic aspects of scientific achievement. The framing of East's achievements within the context of China's national pride and technological ambitions is an important detail that can be missed. The narrative surrounding the artificial sun is not just about scientific progress but also about positioning within the global arena. As countries vie for leadership in advanced technologies, achievements in nuclear fusion can serve as a benchmark for national capabilities. This cultural dimension adds layers of complexity to the scientific advancements, as they are not only technological milestones but also symbols of national identity and ambition. 7. Research collaboration and its importance. The mention of over 120 research institutions in collaboration with East is another detail that may not be fully appreciated. This international network signifies the collaborative nature of contemporary scientific endeavors. The pooling of resources, knowledge, and expertise from diverse geographical and cultural backgrounds can lead to faster and more comprehensive advancements. The potential for cross-pollination of ideas may ultimately enhance the pace of innovation in fusion technology and beyond. Conclusion. In summary, while the immediate achievement of a plasma confinement record at ITER is a remarkable milestone, the deeper implications surrounding ignition, technological innovation, international collaboration, historical context, sustainable energy potential, cultural narratives, and research partnerships are equally, if not more, significant. These elements provide a fuller understanding of the impact of ITER's achievements on both a national and global scale. Recognizing these nuances is essential for appreciating the broader narrative of scientific progress in nuclear fusion and its role in shaping the future of energy. 1. Significance of extended plasma confinement. The achievement of maintaining plasma for 1066 seconds marks a pivotal step towards realizing practical nuclear fusion energy. Extended plasma confinement is essential to reaching ignition, where the fusion reaction produces more energy than it consumes. This milestone not only signifies a technological breakthrough for the ITER reactor but also advances the global pursuit of sustainable energy solutions, potentially transforming energy generation. 2. Technological innovations and upgrades. The success of the ITER reactor was made possible through critical upgrades, such as doubling the output capacity of the heating system while ensuring stability. These technological improvements reflect a significant evolution in fusion research, enabling longer confinement times and enhancing the reactor's efficiency. The advancements at ITER could serve as a model for future fusion reactors, including the ITER project, which faces delays but relies on similar technological foundations. 3. International collaboration and impact. China's active participation in international fusion projects, particularly its collaboration with the ITER program, underscores the global nature of nuclear fusion research. Despite delays in ITER's timeline, the advancements at ITER contribute valuable insights and methodologies that could accelerate the development of fusion energy worldwide. This collaboration fosters knowledge sharing among scientists and strengthens China's role as a leader in nuclear fusion research. 4. Potential for sustainable energy. The breakthroughs achieved at ITER are not merely scientific triumphs, they hold the potential for significant environmental impact. If successfully harnessed, nuclear fusion could provide a virtually limitless clean energy source, addressing the global energy crisis and mitigating climate change. As the world increasingly seeks sustainable energy solutions, the advancements in fusion technology at ITER represent a hopeful pathway toward a greener future. 1. The Manhattan Project 1942–1946. This was a secret U.S. government project during World War II aimed at developing the first nuclear weapons. The project brought together some of the most brilliant minds in physics, including Robert Oppenheimer, Enrico Fermi, and Richard Feynman. The culmination of this project was the successful detonation of the first atomic bomb in 1945 at the Trinity test site in New Mexico. The achievements of the Manhattan Project not only changed the course of the war but also ushered in the nuclear age, profoundly impacting global politics, energy policies, and scientific research. 2. The Tokamak Research 1950s present. The development of the Tokamak concept for nuclear fusion began in the 1950s in the Soviet Union. Tokamaks, which are devices that use magnetic fields to confine plasma in a toroidal shape, have been the foundation of much of the research into controlled nuclear fusion. The first successful Tokamak T1 was built in 1958. Over the decades, various Tokamak experiments, including the Jet Joint European Torus in the UK and the K-Star in South Korea, have sought to achieve sustainable nuclear fusion. These projects have contributed to significant advancements in fusion technology, influencing ongoing international efforts such as ITER. 3. The ITER Project 1985-present. The International Thermonuclear Experimental Reactor ITER is a major international collaborative project aimed at demonstrating the feasibility of nuclear fusion as a large-scale and carbon-free source of energy. Launched in 1985, ITER is being constructed in France and involves contributions from 35 nations including the EU, USA, China, India, Japan, South Korea, and Russia. Once operational, ITER aims to generate 10 times the energy it consumes and is expected to significantly advance fusion technology, paving the way for future commercial fusion power plants. The project has faced numerous delays and budget overruns, but it remains a pivotal endeavor in the quest for sustainable energy. The recent achievement of China's experimental advanced superconducting Tokamak East, which successfully contained plasma for over 17 minutes, marks a pivotal milestone in nuclear fusion research. As we look toward the future, several predictions can be made regarding the potential developments in nuclear fusion technology, its implications for energy production, and its broader impact on society and the environment. Predictions for nuclear fusion development. 1. Accelerated research and development. Following East's record-breaking success, there will likely be an increase in funding and resources devoted to nuclear fusion research globally. Countries and private companies will aim to replicate and build upon China's advancements, leading to faster technological innovations and breakthroughs in plasma confinement techniques. 2. Enhanced collaboration. The collaboration between East and the International Thermonuclear Experimental Reactor ITER will deepen. With both projects sharing knowledge and advancements, global partnerships in fusion research will flourish, spurring advancements that could expedite the transition from experimental to practical applications of fusion energy. 3. Advancements in materials science. Research into materials that can withstand the extreme conditions of fusion reactors will intensify. Innovations in this area will be crucial for the durability and efficiency of fusion reactors, potentially leading to new materials that can enhance safety and performance. 4. Prototyping of commercial fusion reactors. As research progresses, we may see the first prototypes of commercial fusion reactors being developed by the late 2030s or early 2040s. These prototypes will be essential for demonstrating the viability of fusion power as a large-scale energy source. Implications for energy production. 1. Transition to clean energy. The success of nuclear fusion could lead to a significant shift in the global energy landscape. Fusion energy, being a clean and virtually limitless source of power, has the potential to replace fossil fuels and significantly reduce greenhouse gas emissions, aiding in the fight against climate change. 2. Increased energy security. Countries investing in fusion technology might achieve greater energy independence, reducing reliance on imported fossil fuels. This transition will enhance energy security and stabilize energy prices. 3. Integration with renewable energy. Fusion energy may complement existing renewable energy sources like solar and wind. For instance, fusion could provide a stable base load power supply, helping to balance the intermittent nature of renewable sources and ensuring a reliable energy grid. Broader impacts on society and environment. 1. Economic growth and job creation. The fusion energy sector could drive economic growth, creating jobs in research, engineering, construction, and maintenance as new fusion reactors are built and operated. This could lead to the emergence of a skilled workforce in advanced technologies. 2. Global leadership in science and technology. Countries that successfully develop and deploy fusion technology will establish themselves as leaders in the field of energy technology, influencing global energy policies and practices. 3. Public acceptance and policy development. As fusion technology matures, public perception will play a crucial role in its adoption. Effective communication about the safety and environmental benefits of fusion will be necessary to gain public support and influence policy decisions favoring nuclear fusion investment. Challenges ahead. Despite the optimistic outlook, several challenges must be addressed. 1. Technological hurdles. The path to practical fusion energy involves significant scientific and engineering challenges that must be overcome, including achieving sustained ignition and maintaining plasma stability over longer periods. 2. Funding and investment. Continued investment from governments and private sectors is essential. Economic fluctuations or shifts in policy could impact funding for fusion research, potentially slowing progress. 3. Regulatory frameworks. As fusion technology progresses, comprehensive regulatory frameworks will be necessary to ensure safety, security, and environmental protection, which could be a lengthy and complex process. Conclusion. The recent success of China's East Reactor represents a landmark achievement in nuclear fusion research and signals a promising future for clean, sustainable energy production. As the field advances, we can expect increased collaboration, technological innovation, and a significant shift in the global energy paradigm. While challenges remain, the potential for fusion energy to revolutionize how we generate power and combat climate change is immense, making it a crucial focus for scientists, policymakers, and investors alike in the coming decades.